Okay, so let's do this homework problem number, I think it's 4, or maybe 5. Anyway, it's the one where we're going to find a Maclaurin series and then we're going to bound its error for an approximation. So I think the best way to follow along with this video is I will give you a hint and then you will try it and then you can check to see if you've done it correctly by following along. So part A says find the first 4 terms in the Maclaurin series for the integral of sine of x to the 4th dx. So the whole trick here is you have to actually know what the Maclaurin series for sine of x is, and then you make a substitution of x to the 4th into that series. So give that a try. So here's the series for sine x, and now I'm going to make a substitution of x to the 4th into that series. So here I've just replaced the x's with open parentheses, and now I'll substitute in x to the 4th for all of those. Simplifying, we get this series. Alright, and then the last step is we're interested in a series that approximates the integral of that, so now we can just integrate term by term. So here all I've done is I've increased each exponent by 1, so 4 becomes 5, 12 becomes 13, and so on, and then I need to introduce a 1 over that exponent factor in the coefficient, so that way when I take the derivative it will cancel. And there we have our answer. And even though I have a dot 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 here, I've only included the 4 terms that the problem requested, plus the constant of integration on the end. So part B says, use that approximation to evaluate the definite integral from 0 to 1 of sine of x to the 4th dx. So my advice here is just evaluate it the way you would anything. This is the antiderivative, so you've already found that. So now you can just go ahead and evaluate it at 1 minus it evaluated at 0. And here's what the solution looks like on the next page. So we've got the definite integral is the antiderivative evaluated at 1 minus the antiderivative evaluated at 0. So I've just written the antiderivative that we got from part A. As you can see, the constant of integration, as always, cancels itself out. And so now we have this evaluated at 1 minus evaluated at 0. So because all of these terms end up as 0, there's nothing to consider here. And I hope you would have actually seen that without having to write it all out. So let me get out my handy calculator and we'll see what this is equal to. And here's what I have as my solution. I have 0.18756947 and so on. So the problem now is, when we used approximations before, we actually knew what the answer was, so we had an easy way of checking how far off is the approximation from the true value. Here we don't actually know what the answer is, so we'll have to use Taylor's remainder theorem to put an upper bound on the error, and that will tell us how far off could this possibly be. So let's go ahead and bound the error. The first thing I'm noticing is that this is an alternating series, and so we have that really convenient alternating series error bound that we can use. You remember that if you have an alternating series that's convergent, you can bound the error using the magnitude of the next term in the series that you would add. So let's go back and figure out what is that next term in the series. Here was our first page, so let's just go ahead and add another term here. So I had x to the 7th, so that'll be x to the 9th over 9 factorial, which means that when I substitute, I'll have x to the 4th to the 9th power over 9 factorial. And when we simplify that, that's going to be x to the 36th over 9 factorial. And so that gets added to our integral. And I guess I'll write it down here. So once that gets added to our integral, the 36th power becomes a 37th power. So I've got x to the 37, and that's still over 9 factorial. But I need to have a 1 over 37 factor in there. So this is what the next term in the series would be. So now back over here, I know that the magnitude of my error is going to be smaller than what I get when I evaluate that at 1. So it was x to the 37th, so now it's 1 to the 37th, which is really just 1, over 37 times 9 factorial. And that is equal to approximately 0.0000000744. So actually, wow, that is quite accurate.